one of the things that we're going to start seeing with integrations, the truth is you guys have seen basic integration, relatively simple forms of integration, and now it's going to get a lot more complicated, okay? So we're going to start with some of these integration techniques. We're going to start with these advanced integration techniques, and then we'll move on to the inverse trigs. So this is where we're talking about long division. When you've got a fraction, okay, and I don't know if you've done integration with long division before, but looks on your faces, maybe not. So good, new material. When the degree of the numerator is greater than or equal to, you want to divide first. And the reason we're going to divide is because we're going to be able to hopefully separate our integral up into pieces that are easier to integrate. And that's what this is saying here, okay? So once we can separate it out into smaller pieces, more manageable pieces, they become easier to integrate. Yeah, I think you could use synthetic division. It's just clunky. It makes more sense to use long division here because then we can separate our quotient up into the right kinds of parts. So here's the example I want to do for starters. And this is on page 138 in your book. Now, obviously, if this was factorable and that, this was factorable and you could cancel stuff, you look to do that whenever possible. And of course, one of your first thoughts when you look at a problem like this is why maybe I can use substitution. And the fact that the degrees are the same, of course, when you differentiate something like that, you would expect just an x somewhere. I mean, there's one here, but kind of by itself. So substitution is just not going to get you anywhere. So I want you to do this long division. I want you to see if you remember how to do long division of polynomials. No?
Let's try, guys.
Yeah, I think you should try. Here's the setup, okay? Here's your setup. That hopefully gives you a little bit of a hint. Okay, hopefully that gives you a little bit of a hint. Try to remember this. So the thing we have to do first, okay, we just ignore the other terms. You just look at the first term and the first term, and you go, how many times does x squared go into x squared? And of course that answer is 1, and that goes up here. Okay, and then you multiply this by that and subtract, right? That's the regular division algorithm. So x squared plus 2, but then I subtract essentially changes the signs. Okay, so the x squareds cancel out. That should always happen. I still have a minus 4x, and then the 2's cancel.
Wait, hold on. Why do you got plus and minus 2?
Well, when I do my multiplication, I get x squared plus 2, and then I have to subtract. After you multiply, then you always subtract.
So can't you just make it minus? Why you got that?
Yeah, I could, but I already had a plus sign there. You always subtract in the division algorithm. Multiply, then subtract. Okay. Now, this here's where once the degree of your remaining term is less than your divisor, that's where your remainder comes in. So my remainder ends up being just negative 4x over x squared plus 2. Okay. Now, so what we can do now is just integrate this. See, and we end up with a remainder where the degree on the top is now smaller than the degree on the bottom, so we're going to be able to do substitution here. So here's where I'm at, because I'm just going to integrate this. Okay, so this part's really easy. This part will take a little more work, and why don't you try the rest of it? Obviously, this is easy, right? What is the integral of 1? Just x. And there, yeah, and I put a plus c in there. Now here's I didn't actually write out the u substitution, so if you did, that's fine. But what's u going to be over here? X squared plus 2. So du is 2x. So I've got like an extra 2 here. Otherwise, we'd be good. So here's how I manipulated that a little bit. I just basically took a 2 out of that because I know that du is 2x dx. And I just slid the 2 out. This is a little c. Okay. And so since u is this, it's just the natural log of the absolute value of that with the 2. Okay, so the 2 is still there. Natural log of this. Then I combine my c's into one c. Actually, to be honest with you, if I were to do this problem again, I probably wouldn't put this c. I would just leave one c here and leave that one off since I'm going to put them together. But at the end of the day, if I have a constant and another constant, it's just another constant. Okay. Notice something here. Why did I remove the absolute value? Right. This has to always be positive. Now, could you leave the absolute value here? Of course. But I think, as you work through problems like this, you should be trying to analyze your solution a little bit when you can. And so that's why I chose to do that. All right. Are there questions about what we did here? How many of you had something like that? Okay, really good. Good. So while this might be a little painful and require some recall, it allows us to transform this integral into something more manageable. Okay. Let's look at another example. This is example 2, same page. What's different about this than what? What do you mean? Tell me about that.
Like the test. This was like
Close.
Also, wait, why are you writing the answer test?
So this problem, you're right. It starts off pretty innocuous. No big deal. We can just use a little, u substitution. And what should u be? Nope. Squared x. Okay, what's du going to be? Just wait, you'll see. Ooh, tricked you up. Why would you do that? Okay, so here's why we did that. Okay, we did that because we're going to end up having to substitute in here in a second. Okay, so 2u du equals dx. Now, again, doesn't seem like that big a deal so far, but let me show you what this means, what this is like. Okay, right? Dx is 2u du. This is 1 over u minus 1. What should I have to do? The degree on the top and the degree on the bottom are the same. Now use division. Okay. The other techniques that you were talking about, you would have just gotten yourself into a place where it would have got kind of hairy. Had this entire denominator been under the radical, you would have approached this problem differently. But because this radical is by itself, that's why we have to do this. This division is not as bad, right? It just gives me 2, then subtract. Did you get that for your division? So now again, I'm just integrating these pieces, and this will be pretty simple, right? So I've got the integral of 2 plus 2 over u minus 1 du. And this becomes 2u. And then this is 2 times the natural log of u minus 1, or absolute value. Okay. Then I substitute back in, and we're good. We do need to keep the absolute value because it is possible that this number is less than 1, depending on what x is. The key here is the fact, again, that there is a square root on one part of the denominator and not on the other. This is really just the beginning of this advanced integration techniques, because we're going to start seeing a lot more throughout the rest of chapter 6, and it's going to be important for you to figure out when to use what. And you should start being able to recognize it as you work through it, but keep in mind with integration, because there's so many different ways that you can do it, and I know you don't know all the ways yet, but integration is one of those things where if it doesn't work the first time, try a different way. If it doesn't work that way, flip it around and try it another way. One of the things about integration that can be tricky is if you don't catch it right the first time, you might spend a little while on it, and that is not uncommon, okay? I know that is not something you enjoy. You like to know the path, and you want to be on the path, and you want to do the steps, and you want to finish. It doesn't always work like that, okay? All right, the next part, if you recall, we have our trig functions, okay? The derivatives of the inverse functions, the arc functions. Okay. The top ones are your basic ones. The derivative of the arc sine is 1 over the square root of 1 minus x squared. The cosine just has it negative. The arc tangent is just 1 over 1 plus x squared. Okay, and then of course you have all the u versions with the derivative of u, chain rule basically, dealing in your inside function is the derivative of that. Okay. Hopefully you do remember those. If not, write them down and remember those. Now, this next part, all right, is if we integrate both sides, right? If you integrate this side, the derivative part goes away. So the arc sine is the derivative of this. So that's where you have to recognize when it's in one of these forms that the integral of that will be the arc sine, the arc cosine, or the arc tangent. Okay. Now, I will tell you this book really doesn't bother with arc cosine, and I think it's just because it's just a sign change, so you have to watch out for that. But I think the other thing that you can do is if this number up here is negative, you can slide it out front and still have negative arc sine. And so that's why you really don't need to know this one as much. It doesn't come into play. But notice here a couple things. Okay, when I take the integral of both sides here, this is where that comes from. When I take the integral of both sides here, that's where this comes from. And then we have another version of all of that. Okay. If we had a funkier looking fraction, because notice these fractions are ones in them. They're not always going to be ones. Okay. If this a was a 1, then these formulas would look like this, right? If a is 1, then it's just u. If this a is 1, then there's nothing in front of the arctan, and it's just u. But when a is not 1, we still have the ability to calculate the integral of each of these. You just have to account for the a. And you have to account for the a in one place for the arc sine, but you have to account for it in 2 places with the arctangent. Okay? So that's the distinction. When you're dealing with the arctangent, you're going to have this 1 over a out in front. So what I like to do when we do these problems is I want to identify A if it's not 1, and I want to identify U. Because if you identify A and you identify U, and you catch the integral in either of these forms, then it's just a matter of plugging them in. So you need to know this one, you need to know this one. And again, the reason why we see this extra A here and here is because if this front term is not a 1, and it's some other number, that A is just the square root of whatever that number is, okay? All right, so here we're going to go through a couple examples. Let's see. Yeah, we're going to go through 2 examples. All right, so go from your book, number 4. Now this isn't quite in the form that we're used to seeing. Okay. Is this a potential arc sine or arc cosine? Or sorry, arc tangent. All right. It's got a plus and there's no square root. Now I'm going to flip it around so we put it back into that form. You don't have to, you know. And I just went ahead and copied this back here so we can see that it's in that form. All right, so I need to identify A, I need to identify U, because once I do, then I can just slap it into here. All right, so what is A here? 5. So this is A squared, so A is the square root of this. So this can happen even if this isn't a perfect square. Right? If this was 10, then A would just be the square root of 10. Obviously, 25 is a perfect square, so A is 5. What is U going to be here? 2x, right? The square root of this. So I like to write those down. And the thing is there should be, this top should be the derivative of this, but it's not. Right, because the derivative of U is 2dx. Right, so I wanted to have a 2 up here, so I'm gonna slide that over, make it a 1/2, and then I can substitute it because 1 dx is the same as dx. So here's where we're at. So you see how we're combining some techniques together, right? And I color-coded it kind of for you. 25 stays the same. Now my U is U, but U is really 2x. But I can use this to transform it into this form. Okay, so this can be used this way, and I just have this extra 1/2 out there, and then eventually I'll substitute back in. All right, so here's where we go. The orange is the integration of this. So my 1/2 that's still hanging around, my 1/a, arctangent of U, but U is 2x, over a, which is 5. You could stop here, but you know me by now. I can't stop. Can't stop. Won't stop. Okay. Either of these are acceptable. Right, there's a lot going on here. A lot of new stuff. So we first have to get it into the form that looks most like this. Right away we noticed that it couldn't be sine, it had to be arctangent. And then it's just a matter of making it fit. And from there it's integrating this, okay? Yeah, A is always a constant, and it always is going to be in 2 different places here. And that's the 5. It turned into a 10 when I multiplied by this half that we had to do with this substitution. Okay? Other questions? Now, if this was the square root of all of this and a minus, you'd basically do it the same way, and it would be arc sine of 2x over 5. Still u over a. Okay, it's just you don't have this extra 1 over a in front for the sign. Okay, one other type of problem. Getting back to more of your algebra roots. Okay. I've also heard this is a common thing on the AP exam to have to know how to do. To complete the square. Complete the square. Essentially what we're going to do, now this could happen in a sign situation too. If there was a square root underneath here, we could do the same thing. All right. But essentially what we're trying to do is come up with, if possible, 2 perfect squares. Right? There's my a squared, there's my u squared. That's why we're going to complete the square. Okay. So here's the trick, right? It's important to pay attention to this part. This part is your clue about what should be there in order to make it a binomial square. So the question I have for you is, what number would I want to be here in order for that trinomial to be a binomial square? 4. How do you know that it's 4? Half of b and square, right? So whatever this number is, take half of it, which is 2, and then square it. So x squared plus 4x plus 4. Well, I already have 8 here, so I can just break that 8 up, like so. And now, I have, not only do I have a binomial square, but I also have a constant square, a perfect square that's a constant, okay? Now, it's not always going to be that nice, right? Sometimes you might have to add and subtract. Sometimes you'll have a negative somewhere. Those kinds of things, okay? This one I made pretty clean for us. So what does this look like as a binomial square? Yeah, x plus 2 quantity squared. And I wrote it out like this. You could rearrange it and put the 4 in the front, but I think we know which one is a and which one is u, I hope. Okay, which one is a? What is a? 2, right? This is a squared, so a is 2. What will my u be? X plus 2. And then what is du? If u is x plus 2, what's du? Dx. Okay. Again, there's my tangent. I need it. So a is 2, u is x plus 2, du is dx. So this is a clean substitution, right? Which means I don't have to worry about really subbing much in, okay? Since everything is spoken for, I can go straight to here. I didn't have an extra anything on top like we did with the last one. We could really, if we wanted to, we could just rewrite this whole problem if we wanted to. You don't have to. 2 squared plus u squared du. So it's a straight substitution now. I don't have extra terms, and so I can just substitute right in here. For a is 2, u is x plus 2, and that's it. Okay. Again, the 1/2 comes from the 1 over a. The u is x plus 2, and the a is 2. Okay. If I would have had an extra thing like we did with the other one, we'd have an extra number on the outside. But this one is clean, so we're good. That's a good point. I will use this interchangeably. Sometimes I'll write arctan. I don't know. I think it's... Sometimes I'll write it like this, and when I do that, I'm going to throw that in there. They mean the same thing. Yes, either of those are fine. And I suppose it's important to be able to go in between both. Okay. It does not mean 1 over the tangent.